name is Jimmy Nakamura. I work for Professor Mike Manfred at Purdue University. So we're studying quantum Hall states. So we take a two-dimensional electron system. In our case, it's gallium arsenide. We cool it down to low temperatures and apply a strong perpendicular magnetic field. And under those conditions, you get these quantum Hall states where you have zero conduction in the bulk, and all your current is carried by chiral edge states with quantized conductance. Conductance given by the filling factor nu, which is an integer or fraction, times the conductance quantum e squared over h. And the fractional quantum Hall states are predicted to have some special properties. Is that they're predicted to have fractionally charged quasi-particle excitations, which also obey fractional braiding statistics. And what I mean by braiding is you take two quasi-particles and braid one of them in a loop around the other, and you get a Barry phase that's a fraction of 2 pi. And we want to probe these interesting properties through electronic interferometry. So what we're going to do is define an interference path using metal gates on the surface. And the way this is going to work is we send in an edge current from one of the contacts, and it's going to be partially reflected by this quantum point contact. It's a narrow constriction, and so it gets reflected, and then the rest of the current goes on through the device and is reflected at the second quantum point contact. So now we have interference between the two different reflected paths. And the quantum mechanical phase that governs this interference will have two contributions. The first will be the Aronoff-Bohm phase, because we're going around some magnetic flux since we're at high field. And for the fractional case, if you have fractionally charged interfering particles, that Aronoff-Bohm phase will be scaled by the quasi-particle charge. Then the second contribution will be, if we're in a fractional state, and we braid it around some localized quasi-particles in the middle, you'll have a contribution from that. And for the Aronoff-Bohm phase, there's two ways we can control this. So we can change the area by changing the gate voltage to squeeze the device in more, or we can directly change the magnetic field. So if we do the experiment and do those two things, change the magnetic field and gate voltage, the expectation, this is simulated data from a theory paper, is that you'll get lines of constant phase, or what we're measuring is the conductance across the device, that have a negative slope as a function of those two variables. But what tends to happen if you just jump into these experiments naively is you'll get the opposite of the expected behavior. As you change the magnetic field and gate voltage, you'll get constant phase, constant conductance lines with positive slope. So that's unexpected. And the explanation for this is that Coulomb charging effects in these types of devices cause the area to change as you change the magnetic field. So we can't do the clean experiment we want to do where we change area and magnetic field independently. And the other problem with this is that in the regime where you're dominated by Coulomb effects, the braiding becomes unobservable. So this is a problem. So to recover Aronoff-Bohm behavior, what you can do is take your device and put a large gate over the top of the interferometer to screen these Coulomb charging effects. But the problem with this is that in order for this to work well, you need to have a large device so you can have enough capacitance from this top gate in order to screen. The problem with large devices is your quantum coherence is then really poor, so you get low amplitude oscillations, and in particular, we're not able to measure any fractional interference in such large devices. So what we need is a way to suppress Coulomb effects that's more effective so we can make small devices and still have Aronoff-Bohm behavior. So our solution to this problem was to design a gallium arsenide heterostructure that has screening built in. So here I'm showing the layer stack and a simulation of the band and electron densities. So a typical structure used for these sorts of experiments would have a single gallium arsenide quantum well where all your electrons would be. But in this structure, we've included two auxiliary screening wells that also have high electron density in them that are intended to screen the Coulomb charging effects. And this is similar to putting the metal gate on top, except we basically built the screening into the structure. And this is beneficial because we're able to get the setback of the screening wells very small. So we can get better screening because they're close. And we designed this to have high electron density in the screening wells to get good screening. But if you know much about these types of experiments and these types of structures, you'll realize there's a problem with this, which is that we've deliberately introduced a huge amount of parallel conduction. There's actually more charge in the screening wells than in the main well, so that's going to be a problem for our measurements. So if we measure Hall transport, we're probing all three of the wells, whereas we just want to be probing the main quantum well. So to solve this, we borrow a technique that's been used in bilayered quantum Hall systems, where we've included gates that go around the ohmic contacts on top of the chip and on the bottom of the chip in order to selectively deplete the screening wells so we can probe just the main quantum well. So what we do is we negatively bias these gates. So we first negatively bias the top gate, we disconnect the top screening well from the omics, and now we're just probing the quantum well and the bottom screening well. And then if we do the same for the bottom gate that's around the omics, we've disconnected both screening wells from the contacts. So now we get clean quantum Hall transport through just the main quantum well. You can see the quantum Hall plateaus at integers and fractions. But our interferometer is in the middle of this Hall bar, so it's away from those gates where we depleted the screening wells. So the screening wells are still there and available to screen Coulomb effects in the interferometer. And because of that, we've been able to make the device much, much smaller than if you just had a metal gate on top to screen. So the area of our device is about 0.7 micron squares, an order of magnitude smaller than you can get otherwise. Another potential benefit of this screening well scheme is that our simulations indicate that the presence of the screening wells gives you a much sharper confining potential, which can help prevent things like edge reconstruction and give you higher edge state velocity. So that can also be a way to improve the coherence of the interference. So to test and verify that we really are suppressing Coulomb charging effects, what we do is take our device at zero magnetic field and put it into the tunneling regime and measure Coulomb blockade. So what we do is measure the differential conductance, and you get this diamond pattern where the height of the diamond gives you the Coulomb charging energy. And for our device with the screening wells, it's quite small, about 17 microelectron volts. Whereas for a device without screening wells of similar size, it's much larger, something like 200 microvolts. So for proper data visualization, what I should be doing is putting these on the same y-axis scale so you can compare the height of the diamonds. And so if I do that, you can see that it's very dramatic effect. So the screening wells work great at suppressing Coulomb charging. So then the real test is to go to the quantum Hall regime and measure interference. So we first start at integer state u equals 1, robust integer quantum Hall state, and do the experiment. We change the magnetic field and change the gate voltage and measure conductance oscillations. And we see indeed we get a negative slope. So we recover the Aronoff-Bohm regime behavior that we want, even though our device is so tiny compared to what you would otherwise be able to do. And because the device is so small, the quantum coherence is greatly improved. So the interference amplitude, the amplitude here is many kiloohms. So this is very easy to measure, and it's quite robust. So it survives up to hundreds of millikelvin. So making the device small is a great benefit to these types of experiments. And what we do next is go to fractional quantum Hall states. And because we've made the device so small, we're able to measure interference in two of these states, nu equals 1/3 and nu equals 2/3. And I mentioned before that the Aronoff-Bohm phase will be scaled by the quasi-particle charge. So we can extract the interfering charge from the gate oscillation periods. We change the gate voltage. And at nu equals 1/3, we measure a fractional charge of about 0.29. So that would be consistent with the theoretical value of E over 3. Now at nu equals 2/3, we measure something close to the integer charge, about 0.93, which might seem surprising. You say, oh, it's a fractional state, so maybe it should have a fractional charge. But one of the simplest possible edge structures for the nu equals 2/3 state, 2/3 is kind of the particle hole conjugate to 1/3. So it could have a outer nu equals 1 integer charge mode and then a counter-propagating 1/3 charge mode. So in that case, it might be that in our interference experiment, we're only sensitive to the integer charge one. But this is not the end of the story on 2/3. It's a complicated state. There's several other theoretical models for the edge structure, and it's a very active area of research and experiments and theory. So our conclusions. The main result is that we've succeeded in dramatically suppressing Coulomb charging effects in these devices, such that we're able to make small devices that have really good coherence, and we're able to measure interference of fractional quantum Hall states. And something else, I didn't get into this, but we were also able to measure the edge state velocity of integer quantum Hall states, including inner modes that are part of the measured interference work, and match those with numerical results. But there's still a lot we want to do. So we want to be able to do the experiment of measuring the braiding statistics. So we want to make devices where we can control localized quasi-particles in the middle of the device. And we'd also like to explore the limits of screening. So see how much smaller we can make these devices before they succumb to Coulomb effects again. And then, of course, the great thing about quantum Hall is there's a huge number of states out there to study. So it would be great if we could extend interference to higher order fractional quantum Hall states. Thanks for your attention.
Questions from Jeff?
So you mentioned really low charge energy. So it seems that when you change magnetic fluxes, maybe more favorable just for charges of basically particle. So I wonder how much do you need to what relative change of the magnetic field you need to actually introduce this particle inside?
Well, so he was asking about, since we reduced the charging energy quite a bit, how we're going to induce quasi-particles, or how much magnetic field we would need. And I'm not, in terms of magnetic field, I'm not sure, but our approach for going forward is going to be to include gates in the middle to do it electrostatically, directly. So I'm not sure about the magnetic field dependence.
The one in the back.
Have you seen the same behavior for 2/3 other samples? And also, have you gone on to 3/5 and 2/5? Robust number.
So at 2/3, we haven't looked at that. We have reproduced interference at 1/3 in another device. We haven't looked at 3/5.
One last question.
This is very nice data.
Thank you.
Nice device. It's obviously very cold as well. I was wondering if you looked at the temperature dependence of the oscillations at all to see, like, if you were either warmer, would you still see them?
Yes, so at nu=1, we did that exact experiment. So measure the sort of coherence of the oscillation versus temperature. It shows something like a 200 millikelvin decay scale.
Or whatever, for the fractions then?
We haven't done that yet.
Oh.
Right, I think with that we thank the speaker and thank all the speakers.